Hi everyone, so we're going to continue talking about the photoelectric effect, and if you remember from the previous video we were talking about the differences in terms of the observations that were actually made on the photoelectric effect experiment versus what was predicted by classical physics. Okay, so what we're going to do now is basically present this theory by Einstein that actually explain how to look at the photoelectric effect. And what Einstein did was basically the following. So if you think about the plot here, remember that we were discussing this, that the energy of the electron that's ejected off the surface of the metal, right? Remember that the electrons are all ejected off the surface of the metal. So we remember that there was a requirement, there's a frequency requirement for that electron to be ejected, okay? And we call that the threshold frequency, or given the symbol nu naught. Remember this symbol right here. And once you reach that frequency, if you go above that frequency, then what's going to happen is the kinetic energy of the electron will just keep going up proportionally as a function of frequency, okay? So what Einstein did was people were not able to explain these observations for many years because, again, classical physics failed to predict really anything that's actually observed experimentally. So what Einstein did was he said, well, let me take the plot of the photoelectric effect, which is the plot of kinetic energy versus the incoming light frequency, and kind of put the plot for several metals all into one plot, okay? And so that's what he did here. He combines the kinetic energy versus the frequency plot for various metal. In this case, I'm listing rubidium, potassium, and sodium all in one. And remember that each plot basically looks like this, right? There's kind of a flat line at the x-axis, and then at some point there is a frequency, right? Because this is the x-axis, here is the frequency axis. So at some point there's a frequency that allows the electron to be ejected off, and once it's ejected off, then the kinetic energy of the electron is just proportional to the frequency. And as you can see there, for potassium, the nu naught value, the threshold frequency is a lot higher. So it takes a higher frequency light in order to eject the electron off potassium, and for sodium it's even higher, so nu naught is even higher. So what you look at right now is just going to consider the top part of this curve, because basically this is the same curve that the one we saw here, except now he put three metals here. So it would be like one is this one, the second one, the nu naught is a little further, it goes up like that, and the third one, the nu naught goes even further, so it goes up that way. Okay, so that's the three different metals. And then what he did was that he said, well, what happens if I were to extrapolate? So I take that line, right, the nu naught line, and I just extrapolate this line all the way to the y-intercept for all three graphs, okay? And what he found was that when he extrapolated this to touch the y-axis and found the y-intercept for this equation, he found that the value of that y-intercept is equal to nu naught, okay? And it's negative because this is a negative part of the y-axis. It's negative of nu naught times a value, 6.626 times 10 to the minus 34. And of course, if you he's been reading up on the recent literature about discoveries in the physics world, and he remembered that that number was the same number that Planck proposed to be his fitting constant for the energy of black body radiation, right? Energy of the black body radiation given a certain frequency. So he realized that that number is important because that's the same number that Planck also discovered. Not only that, if he were to look at the slope, you can see that all these lines, they all have the same slope, right? They all are oriented the same way. That means they all have the same slope. When he looked at the slope of this line, he realized that all the slope are equal to the value of h, which is 6.626 times 10 to the minus 34 joules second. So then he realized he's onto something, because all of the slope are the same value. All of the y-intercept really have the same expression, which is negative h times the nu naught for that specific metal. So in this one, the green one would be negative h nu naught for rubidium. This one is negative h nu naught for potassium, and this one is negative h nu naught for sodium. So then what he said was that, well, this is just equation of a line, y is equal to mx plus b. So then what he said was that I can just rewrite this as y is kinetic energy, right? That's the y-axis. X is frequency, nu in this case. So let me fix that a little bit. It's just nu, okay? X is nu, okay? Remember that the slope value, the h, we just say, I mean the slope value m, right? M is slope, is equal to Planck's constant, so it's just kinetic energy is equal to h times nu. And then the y-intercept, b here, has the value of negative h nu naught, so he just plug in negative h nu naught for the y-intercept. So as a result of just fitting the data using an equation of a line, he was able to find this relationship, this equation now, which relates the kinetic energy of the electron that's ejected off the surface of a metal to the energy of the incoming light. Because what is this number, h nu? Well, of course, it's the energy of the incoming light, because remember that that's what Planck proposed, right? E energy is equal to nh nu, so if it's just h nu, that means it's the energy of one of these light packet, okay? So Einstein at that point realized that in the photoelectric effect experiment, you can't really think about light, given this equation, right? Given this equation at the bottom, you can't really think about light in the sense of a wave hitting the surface of the metal like this. Instead, and you know, ejecting the electron off. Instead, what you should think about is that light comes in these packets, the packet that Planck was proposing in terms of the energy of light. It comes in these packets. Later on, these are what we call photons. So light is composed of this stream of particles. Each particle is called a photon. Okay, the particle of light is called a photon. And when the photon hits the electron, it transfers energy. That energy is transferred. If the energy is enough, if there's enough energy, then it's able to take the electron off the surface of the metal. Because remember that the electron is being held by the nuclei of the atoms of the metal, right? So the electron is being held together by this electrostatic interaction. But if the light photon has enough energy, then it's able to hit it, you know, with high enough energy that the electron actually is taken off the surface of the metal. Okay, so what is the big change then in the view of light? Well, the big change is that in this particular experiment, you can't look at light as waves, because if you try to explain the behavior of light like as using wave equations, it's not gonna, you know, you're making all these predictions, which are all the classical predictions, and none of them match the experimental observation. The only way you can you know, explain how this thing works is if you're making the assumption that light you know, is composed of particles, and these particles have energy which is equal to h nu, which is given by that equation right there, Planck's equation. Okay, now what about this h nu naught? Well, think about it, right? If you want to get the, you know, if you want to get the electron off the surface of the metal, the electron is held by this electrostatic interaction of the nucleus, right? Nucleus and the electron is, the electron is held by the nucleus. So it's like a glue. Okay, so you think about, there's a glue that's, or you know, like a magnetic, you think about a magnet, maybe it's a little bit more appropriate analogy. There's a magnet that's holding the other magnet. Okay, one is the nucleus, the other one is your electron. Now, I try to, you know, imagine that you try to rip apart this magnet, okay? If I only put a little bit of amount of energy, the magnet will not come off. But if I put enough energy, at some point the magnet will come off, right? If I put enough energy to ripping off these two magnets. So he say that that's the same idea. There's a certain amount of energy that's kind of holding the electron to the nucleus. So your light photon has to have energy at least equal to that energy that's holding the electron to the nucleus, or higher. And that energy that's holding the electron to the nucleus, it's what's given by this quantity right here, h nu naught. Okay, and that's why it's different for each metal, because each metal, depending on where the electron is located, and we'll get to this, you know, at the end of this topic, really at the end of topic 7, when we start to talk about the electron configuration, and then, you know, valence electrons, location of valence electrons, and so on. it's really what this is saying is that, for that electron that you're going to take off from rubidium, it's a lot easier to do that in comparison to the electron that you need to take off from sodium. So somehow the electron in sodium is being held more tightly than the electron in rubidium. And we would explain why this is, but obviously, if you think about it, it has something to do with the structure of rubidium versus the electronic structure of sodium. Somehow the electron in sodium must be attracted to the nucleus more strongly than the electron in rubidium. And that tells us something about how rubidium is structured, how sodium is structured, how potassium is structured. So what he's saying by this equation is really the following. The amount of energy the electron will have after it gets off the surface of the metal will depend on how much energy the light photon has originally, the light photon that hits the surface of the metal, minus the amount of energy that's holding the electron to the metal. And that should make sense, right? So this is incoming energy. This is the energy that you have to take out in order to get the electron off the surface. So if you subtract this by that, whatever's left should be the kinetic energy of the electron, because then the electron will just travel, right? There's no potential energy at that point because the electron no longer has the electrostatic interaction with the nucleus. The only thing the electron has at that point, the only energy the electron has is this kinetic energy of motion, because it gets off the surface of the metal. Okay. In the next example, we'll kind of re-summarize this discovery and this theory of Einstein and do an example on that.